Hello children, welcome back to chemistry session. In previous session we have seen point defects. In that we have discussed about stoichiometric defect. In today's session we are going to discuss about impurity defect and non-stoichiometric defect. Let us start today's session. Impurity defect. What is meant by impurity defect? We are very familiar with the word impurity. Impurity means unwanted substances present in the given substance. That's unwanted substance is known as impurity. What is meant by impurity defect? Impurity defect means, suppose when the crystallization of molten salt, let us say, during crystallization of molten NaCl means which contain less amount of water molecule. So during crystallization of molten NaCl crystal, we might have observed few crystals of strontium chloride. The strontium chloride is present in it is a impurity present here. Few crystals of a little amount of strontium chloride is present in the sodium chloride. So during crystallization process, some of the lattice sites of sodium in crystal lattice, some of the sodium lattice are occupied by the strontium ion. This strontium ion displaces two sodium lattice. So the strontium ion removes, or in crystal lattice, two lattice sites or lattice points of sodium ion are replaced by the strontium ion. So in that, one lattice point is occupied by the strontium atom and another one is vacant lattice point. It is something like this. Let us talk about NaCl crystal. Suppose it is a crystal of NaCl. Here sodium cation and chloride ion. Sodium cations and chloride ions. Sodium cation. Here, during crystallization of molten NaCl containing strontium chloride as impurity, the strontium chloride, the strontium ion removes two sodium cation lattices. In that, one lattice point is occupied by the strontium ion and another lattice point is vacant. Because strontium valence is specified, it can remove two sodium cations from the NaCl crystal. So this kind of defect is called as impurity defect. I am repeating children. Impurity defect causes when unwanted substances are present in the given substance. Suppose during crystallization of molten sodium chloride, it contains little amount of strontium chloride. Then the sodium cations present in the lattice which are displaced by the strontium ion, and the strontium ion removes two lattice points. Two sodium cation lattice sites. In the one occupied by the strontium ion and another lattice point is vacant. So this is called as impurity defect. It is observed in crystal lattice. It is the one of the defect. The third one, non-stoichiometric defect. Non-stoichiometric defect means this non-stoichiometric defect disturbs the stoichiometry of the metals. In last video, I have told you stoichiometry. Stoichiometry means required number of constituent particles present in the crystal lattice. So non-stoichiometric means the crystals may not have required composition in them. That's called non-stoichiometric defect. This is classified into two types. One is metal excess defect. Metal excess defect. And second one, metal deficiency defect. Metal deficiency defect. So non-stoichiometric defect disturb the stoichiometry of the metals, which is classified into metal excess defect and metal deficiency defect. Let us talk about them. First one, metal excess defect. How does metal excess defect arises? This metal excess defect arises due to anionic vacancies. When the metal containing less amount of anionic sites in the crystal lattice, then this metal excess defect arises. We know that ionic solids contains equal number of cations and anions. For example, sodium chloride. It's a ionic solid. When we heat sodium chloride in an atmosphere of sodium atmosphere. When we heat sodium chloride crystal in a sodium atmosphere, then this sodium chloride is dissociated to sodium cation. So it gives out sodium cations. And these sodium cations are present on the surface of the crystal layer. And the sodium cations which are present on the surface of the crystal layer, they combine with the chloride ions. Chloride ion is Cl minus Cn. Then chloride ions are diffused over the surface of the metal crystal. Then chloride ions combine with sodium cations to form sodium chloride, Na plus Cl minus, which gives NaCl salt. Because on heating sodium crystal in a sodium atmosphere, which gives out sodium cations, which are placed over the metal surface layer. Then chloride ions diffuse over the sodium chloride crystal layer. Then chloride ions are combined with sodium cations to form sodium chloride. So during this process, sodium atom release electrons. Those electrons are diffused into the crystal lattice. It is something like this. Cation, anion. Cation, anions. Because ionic solids are made up of ions, cations and anions. So it's something like this. So in this crystal, they contain excess amount of cations. They contain more amount of cations. And when sodium metal loses electron, when sodium releases electron, the electrons are diffused into the crystal lattice, or the electrons resides anionic portion in the crystal lattice. And during this process, number of cations are more in the crystal lattice. Number of cations are more in the crystal lattice compared to number of anions. So anions number is less, and the free electrons or unpaired electrons occupy the anionic portion. It is like this. It is denoted by F. It is denoted by F. F means the position which is occupied by the unpaired electron, on the side which is occupied by the unpaired electron. So this contains unpaired electron or free electron. This F is called as Farbengen center. Farbengen center. This is causes for appearance of color or producing color, or it is also called as color cell. Farbengen center means it's a German word. It means it is color side because of the electron, the unpaired electron or single electron present in the crystal lattice. This electron absorbs energy from the visible light and gets excited when it gets excited, it emits radiation. That is the reason why sodium chloride appears in yellow color. Sodium chloride gives out yellow radiation because the electron or the carbon center which gets energy from the surroundings and get excited and it gives out yellow color because of the extra cations. Extra cations are present in the sodium chloride crystal. Similarly, lithium chloride. Lithium chloride, due to extra cations are present in the lithium chloride produce pink color. That's why during excitation process, lithium salts produce pink color radiation because it absorbs energy from the visible light. And potassium chloride produce lilac color. Lilac or violet color radiation. This is because initially they do not contain any color, they are colorless salt. Due to the excitation of unpaired electron in the crystal lattice and due to excess cations present in the crystal lattice, sodium chloride gives yellow color and lithium chloride produce pink color and potassium chloride produce lilac or violet color radiation because they absorb energy from the visible light and gives out the radiation. This is called as metal excess defect. This metal excess defect due to extra cations are present in the crystal lattice. These extra cations are the responsible for the giving out radiation are also called as F center, means Farbingen center, which is color site in the crystal lattice. Next, metal deficiency defect. It is difficult to prepare the metals which have stoichiometric composition or stoichiometric proportion because practically it is not possible to prepare the metals which are present in the crystalline solids or crystal lattices. They must contain required amount of stoichiometric proportion. For example, if we have considered FeO, ferrous oxide, the stoichiometric proportion of iron in FeO is 0.95%. But actually it varies from 0.93 to 0.96. So in FeO metal, in FeO ferrous oxide crystal, the variation of iron ranges from 0.93 to 0.96. So it is varies. It may not have stoichiometric composition or particular composition of the metal. This is due to some of the electrons, some of the ions changes from +2 to +3. Because in FeO ferrous oxide, iron has +2 oxidation number, but the oxidation number of the iron is changes from +2 to +3. That's why the variation of the metal percentage in FeO is also changes from 0.93 to 0.96. This means it contains less amount of metal or metal deficiency. This is called as metal deficiency defect. These are impurity defect and next non-stoichiometric defects. These are again two types: metal excess defect and metal deficiency defect. So this is about point effects. So the solid state chapter has completed, children. You have to complete exercise questions and in-test questions from the solid state chapter. And we had binding properties and what types of magnetism: paramagnetism, diamagnetism, ferromagnetism, ferrimagnetism. That is not mentioned in revised syllabus. So all of you go through the revised syllabus, children. According to the revised syllabus, I am teaching here. So this solid state chapter, children. I hope you understand this chapter. If you have any doubts, you can contact me. We'll meet in next session, children. Hope you have to complete exercise questions from the solid state chapter. I hope you understand the chapter. We'll meet in next session. Thank you.